The Space Shuttle solid rocket boosters were the first solid-fuel motors to be used for primary propulsion on a vehicle used for human spaceflight, and provided the majority of the Space Shuttle's thrust during the first 2 minutes of flight. After burnout, they were jettisoned and parachuted into the Atlantic Ocean, where they were recovered, examined, refurbished, and reused. The SRBs were the most powerful rocket motors ever flown. Each provided a maximum 13,800 kilonewtons thrust, roughly double the most powerful single-combustion chamber liquid-propellant rocket engine ever flown, the Rocketdyne F-1. With a combined mass of about 1,180,000 kilograms, they comprised over half the mass of the shuttle stack at liftoff. The motor segments of the SRBs were manufactured by THE of Brigham City, Utah, which was later purchased by ATK, the prime contractor for most other components of the SRBs, as well as for the integration of all the components and retrieval of the spent SRBs, was USBI, a subsidiary of Pratt & Whitney. This contract was subsequently transitioned to United Space Alliance, a limited liability company joint venture of Boeing and Lockheed Martin. Out of 270 SRBs launched over the shuttle program, all but 4 were recovered, those from SDS-51L and SDS-4. Over 5,000 parts were refurbished for reuse after each flight. The final set of SRBs that launched SDS-135 included parts that flew on 59 previous missions, including SDS-1. Recovery also allowed post-flight examination of the boosters, identification of anomalies, and incremental design improvements. Overview. The 2 reusable SRBs provided the main thrust to lift the shuttle off the launch pad and up to an altitude of about 150,000 feet. While on the pad, the 2 SRBs carried the entire weight of the external tank and orbiter and transmitted the weight load through the structure to the mobile launch platform. Each booster had a liftoff thrust of approximately 2,800,000 pounds force at sea level, increasing shortly after liftoff to about 3,100,000 lbf. They were ignited after the 3 Space Shuttle main engines' thrust level was verified, 75 seconds after SRB separation. SRB apogee occurred at an altitude of approximately 220,000 feet. Parachutes were then deployed and impact occurred in the ocean approximately 122 nautical miles downrange, after which the 2 SRBs were recovered. The SRBs were the largest solid propellant motors ever flown and the first of such large rockets designed for reuse. Each is 149.16 feet long and 12.17 feet in diameter. The SRBs committed the shuttle to liftoff and ascent flight, without the possibility of launch or liftoff of sent aboard, until both motors had fully and simultaneously fulfilled their functions, consumed the propellants, were producing zero net reaction thrust, and had been jettisoned by explosive jettisoning bolts from the remainder of the vehicle launch stack. Only then could any conceivable set of launch or post-liftoff abort procedures be contemplated. In addition, failure of an individual SRB's thrust output or ability to adhere to the designed performance profile was not survivable. Each SRB weighed approximately 1,300,000 pounds at launch. The 2 SRBs constituted about 69% of the total liftoff mass. The propellant for each solid rocket motor weighed approximately 1,100,000 pounds. The inert weight of each SRB was approximately 200,000 pounds. Primary elements of each booster were the motor, structure, separation systems, operational flight instrumentation, recovery avionics, pyrotechnics, deceleration system, thrust vector control system, and range safety destruct system. While the terms solid rocket motor and solid rocket booster are often used interchangeably, in technical use they have specific meanings. The term solid rocket motor applied to the propellant, case, igniter and nozzle. Solid rocket booster applied to the entire rocket assembly, which included the rocket motor as well as the recovery parachutes, electronic instrumentation, separation rockets, range safety destruct system, and thrust vector control. Each booster was attached to the external tank at the SRB's aft frame by two lateral sway braces and a diagonal attachment. The forward end of each SRB was attached to the external tank at the forward end of the SRB's forward skirt. On the launch pad, each booster also was attached to the mobile launcher platform at the aft skirt by four frangible nuts that were severed at liftoff. The boosters were composed of 7 individually manufactured steel segments. These were assembled in pairs by the manufacturer and then shipped to Kennedy Space Center by rail for final assembly. The segments were fixed together using circumferential tang clevis and clevis pinned fastening, and sealed with 3 O-rings and heat-resistant putty components. Hold-down posts. Each solid rocket booster had 4 hold-down posts that fit into corresponding support posts on the mobile launcher platform. Hold-down bolts held the SRB and launcher platform posts together. Each bolt had a nut at each end, the top one being a frangible nut. The top nut contained 2 NASA standard detonators, which were ignited at solid rocket motor ignition commands. When the 2 NSDs were ignited at each hold-down, the hold-down bolt traveled downward because of the release of tension in the bolt, NSD gas pressure and gravity. The bolt was stopped by the stud deceleration stand, which contained sand. The SRB bolt was 28 in long and 3.5 in diameter. The frangible nut was captured in a blast container. The solid rocket motor ignition commands were issued by the orbiter's computers through the master events controllers to the hold-down pyrotechnic initiator controllers on the mobile launcher platform. They provided the ignition to the hold-down NSDs. The launch processing system monitored the SRB hold-down picks for low voltage during the last 16 seconds before launch. Pick low voltage would initiate a launch hold. Electrical power distribution. Electrical power distribution in each SRB consisted of orbiter-supplied main DC bus power to each SRB via SRB buses labeled A, B and C. Orbiter main DC buses at B and C supplied main DC bus power to corresponding SRB buses at B and C. In addition, orbiter main DC bus C supplied backup power to SRB buses A and B, and orbiter bus B supplied backup power to SRB bus C. This electrical power distribution arrangement allowed all SRB buses to remain powered in the event one orbiter main bus failed. The nominal operating voltage was 28 plus or minus 4 volts DC. Hydraulic power units. There were 2 self-contained, independent hydraulic power units on each SRB. Each HPU consisted of an auxiliary power unit, fuel supply module, hydraulic pump, hydraulic reservoir and hydraulic fluid manifold assembly. The APUs were fueled by hydrazine and generated mechanical shaft power to drive a hydraulic pump that produced hydraulic pressure for the SRB. SRB hydraulic system. The two separate HPUs and two hydraulic systems were located on the aft end of each SRB between the SRB nozzle and aft skirt. The HPU components were mounted on the aft skirt between the rock and tilt actuators. The two systems operated from T-28 seconds until SRB separation from the orbiter and external tank. The two independent hydraulic systems were connected to the rock and tilt servo actuators. The HPU controller electronics were located in the SRB aft integrated electronic assemblies on the aft external tank attach rings. The HPUs and the fuel systems were isolated from each other. Each fuel supply module contained 22 pounds of hydrazine. The fuel tank was pressurized with gaseous nitrogen at 400 psi, which provided the force to expel the fuel from the tank to the fuel distribution line, maintaining a positive fuel supply to the APU throughout its operation. In the APU, a fuel pump boosted the hydrazine pressure and feeds it to a gas generator. The gas generator catalytically decomposed the hydrazine into hot, high-pressure gas. A two-stage turbine converted this into mechanical power, driving a gearbox. The waste gas, now cooler and at low pressure, was passed back over the gas generator housing to cool it before being dumped overboard. The gearbox drove the fuel pump, its own lubrication pump, and the HPU hydraulic pump. As described so far, the system could not self-start, since the fuel pump was driven by the turbine it applied fuel to. Accordingly, a bypass line went around the pump and fed the gas generator using the nitrogen tank pressure until the APU speed was such that the fuel pump outlet pressure exceeded that of the bypass line, at which point all the fuel was supplied to the fuel pump. When the APU speed reached 100%, the APU primary control valve closed, and the APU speed was controlled by the APU controller electronics. If the primary control valve logic failed to the open state, the secondary control valve assumed control of the APU at 112% speed. Each HPU on an SRB was connected to both servo actuators on that SRB. One HPU served as the primary hydraulic source for the servo actuator, and the other HPU served as the secondary hydraulics from the servo actuator. Each servo actuator had a switching valve that allowed the secondary hydraulics to power the actuator if the primary hydraulic pressure dropped below 2050 psi. A switch contact on the switching valve closed when the valve was in the secondary position. When the valve was closed, a signal was sent to the APU controller that inhibited the 100% APU speed control logic and enabled the 112% APU speed control logic. The 100% APU speed enabled one APU HPU to supply sufficient operating hydraulic pressure to both servo actuators of that SRB. The APU 100% speed corresponded to 72,000 revolutions per minute, 110% to 79,200 revolutions per minute, and 112% to 80,640 revolutions per minute. The hydraulic pump speed was 3,600 revolutions per minute and supplied hydraulic pressure of 3,050 plus or minus 50 psi. A high-pressure relief valve provided overpressure protection to the hydraulic system and relieved at 3,750 psi. The APUs, HPUs and hydraulic systems were reusable for 20 missions. Thrust vector control. Each SRB had two hydraulic gimbal servo actuators to move the nozzle up, down and side to side. This provided thrust vectoring to help control the vehicle in all three axes. The ascent thrust vector control portion of the flight control system directed the thrust of the three shuttle main engines and the two SRB nozzles, to control shuttle attitude and trajectory during liftoff and ascent. Commands from the guidance system were transmitted to the ATVC drivers, which transmitted signals proportional to the commands to each servo actuator of the main engines and SRBs. 4 independent flight control system channels and 4 ATVC channels controlled 6 main engine and 4 SRB ATVC drivers, with each driver controlling one hydraulic port on each main and SRB servo actuator. Each SRB servo actuator consisted of 4 independent, 2-stage servo valves that received signals from the drivers. Each servo valve controlled one power spool in each actuator, which positioned an actuator ram and the nozzle to control the direction of thrust. The 4 servo valves in each actuator provided a four-summed majority voting arrangement to position the power spool, with 4 identical commands to the 4 servo valves. The actuator four-sum action prevented a single erroneous command from affecting power ram motion. If the erroneous command persisted for more than a predetermined time, differential pressure sensing activated a selector valve to isolate and remove the defective servo valve hydraulic pressure, permitting the remaining channels and servo valves to control the actuator ram spool. Failure monitors were provided for each channel to indicate which channel had been bypassed. An isolation valve on each channel provided the capability of resetting a failed or bypassed channel. Each actuator ram was equipped with transducers for position feedback to the thrust vector control system. Within each servo actuator ram was a splashdown load relief assembly to cushion the nozzle at water splashdown and prevent damage to the nozzle. Flexible bearing rate gyro assemblies. Each SRB contained 3 rate gyro assemblies, with each RGA containing 1 pitch and 1 yaw gyro. These provided an output proportional to angular rates about the pitch and yaw axis to the orbiter computers and guidance, navigation and control system during first stage ascent flight in conjunction with the orbiter roll rate gyros until SRB separation. At SRB separation, a switchover was made from the SRB RGAs to the orbiter RGAs. The SRB RGA rates passed through the orbiter flight-after multiplexes, demultiplexes to the orbiter GPCs. The RGA rates were then mid-value selected in redundancy management to provide SRB pitch and yaw rates to the use of software. The RGAs were designed for 20 missions. Propellant. The rocket propellant mixture in each solid rocket motor consisted of ammonium perchlorate, atomized aluminium powder, iron oxide (PBAN), and an epoxy curing agent. This propellant is commonly referred to as ammonium perchlorate composite propellant, or simply APCP. This mixture gave the solid rocket motors a specific impulse of 242 seconds at sea level or 268 seconds in a vacuum. The main fuel, aluminum, was used because it has a reasonable specific energy density of about 31.0 megajoules per kilogram, but a high volumetric energy density, and is difficult to ignite accidentally. The propellant had an 11-point star-shaped perforation in the forward motor segment and a double truncated cone perforation in each of the aft segments and aft closure. This configuration provided high thrust at ignition and then reduced the thrust by approximately a third 50 seconds after liftoff to avoid overstressing the vehicle during maximum dynamic pressure.